Okay, good afternoon. I'd like to welcome everybody to this doctoral thesis or Dr. Techn's defense. And of course, a particular welcome to the doctoral candidate, Anne Ladegaard Skov, who is sitting here and whom I'll invite to the podium in a little while. I'd like also to bid a special welcome to the two official opponents, Dr. Andreas Köllenberger from Wacker Chemie in Germany, and Professor Herbert Schier from the École Polytechnique Fédérale de Lausanne in Switzerland. And also a welcome to Professor Niels B. Larsen from the Department of Micro and Nanotechnology, who together with the opponents are forming the assessment committee, and Niels is also chairing that committee. So these, and perhaps I should also say that my name is Rasmus Larsen. I'm the provost and chief academic officer of this university, and I'll be the chairman of the proceedings here today. And the proceedings will be as follows. So after this small introduction, the candidate will come to the podium and present her thesis, Silicone-based Dielectric Elastomers, in a lecture of approximately 30 minutes. And thereafter, I'll invite the opponents to the podium to discuss the thesis with the candidate. And after that, there will be the opportunity also to ask questions from the auditorium. And after those discussions, the formal part of the defense will be over, and DTU would like to host, or will host, a small reception in the lobby just outside, and I hope you all will join us there at that time. So before we begin, I'd like to say that a very dominating agenda these years is how digitalization changes every industry, every product, every service, and almost every human endeavor. We can see how information and communication technology, the big data and the Internet of Things brings new opportunities to engineering areas, and this fills a lot in the public debate. And sometimes one feels that other basic science disciplines that are almost as impacting are forgotten, and this goes, of course, for biology. Biology and bioengineering also brings opportunities that will disrupt all engineering fields. Bio-inspired solutions, the confluence of electronics and biology, and as I heard the other day, also self-healing concrete, where bacterial processes secrete minerals that close micro cracks in concrete. Just to mention an example that I hadn't foreseen. Material science is also such a field that will affect all engineering areas. New materials with amazing and sometimes unexpected properties will emerge and give us new possibilities for engineering products. And today we will learn something about such materials, about transductive polymers, amorphous structures that can transform electrical energy to mechanical energy, and vice versa, with implications for new sensor systems and robotic devices that can utilize the inherent softness and compliance of the polymer materials. And with this, I would like to invite Anne Ladegaard Skov to the podium to give a presentation of her doctoral thesis work.
Yes, thank you for the very nice introduction. And as Rasmus said, the title of my talk is Silicone-based Dielectric Elastomers. What I will be talking about are what are actually silicone-based dielectric elastomers, what are they, what can they do potentially, and why did we actually choose to work with silicone. Then I will talk very briefly about where the majority of our work has been in how we actually improve the properties of our dielectric elastomers, and also talk briefly about where I think in the future we will go. And then I will proceed to talking about reliability of dielectric elastomers and how do we actually ensure that we have reliable elastomers. So a dielectric elastomer consists of an elastomer, usually thin. It's comparable to Vita wrap films. It's just even more complicated because it's very stretchable, it's very elastic. And then we have compliant electrodes on, and when we apply a voltage over the electrodes, we will see a dimensional change of our elastomer, and then we can actually see that we create electrical energy into mechanical energy. We can also do it opposite way, where we simply actuate our material, and then we can get electrical energy out of that. That's the generator mode. We can also use it for sensing, so we can stretch it and then we can read the capacitance and get a measure out about the deformation. And when we talk about dielectric elastomers and why are they so great, why are they a new type of transducer, it's simply most of where it sort of excel is that we have a lightweight material, we have very stretchable materials, it's a strong material. And just to put Pippi Langstrømpe, my childhood hero, she's actually able to carry like one big horse. If we sort of do the same analogy for our dielectric elastomers, Pippi should actually be able to carry 10 horses. Also in the illustration we have the small monkey riding along, and I think all the good things we have from the dielectric elastomers are also the issues that actually create issues for us when we process, when we formulate. So much of this talk will actually be how we get rid, like we will have to carry the 10 horses around, but we will try to get rid of the monkeys. For me, the product, a dielectric elastomer, the product is a film with compliant electrodes, but of course then other people, they proceed, they make it into products. And for example, in the sensing technology by LEAP technology, usually it's one film that is used for the sensing purposes. Herb Scheer's group also made a rotating motor. Again, I think it was a single film. But if we go into larger products where we see a big commercial potential, then they are usually stacked, fold, or rolled. So every single layer may have some defects and so forth, but if we see a breakdown there, then we will actually put it out through the material or the product itself. So why did we choose silicone elastomers? They consist of the polydimethylsiloxane unit. We have long polymers. They're very soft, they're very flexible, they are thermally stable, and many other good properties. And then what we do is we simply cross-link it. Usually we add some silica, which is shown up there, and then we get our elastic material, which we can use for the energy transduction. When we talk about silicone elastomers or silicone dielectric elastomers, then we are up against some other competitors. Acrylics, usually illustrated by the VHB tape from 3M. It's the double adhesive, which is used to a large extent to showcase what can we actually do with this type of materials, simply because they can show actuation up to 2,000%. But on the other hand, by far that exceeds what we can get out of silicone elastomers. But on the other hand, we don't have any reliability. We can see that after, for example, 10, 100, 1,000 cycles, we will end up having a very different material than the original we worked with. So it's a good material to make demos, but it's definitely not a good product or a material to make a product out of. Then we have the polyurethane, and I think where they really suffered was that they simply changed properties when we have humidity present. So that also led to why I included the water uptake in the spider web. So the silicones are blue, and it position on the outer part of the spider web is really good. And we can see we don't have any problems with water uptake, temperature stability, lifetime, need for pre-stretch that complicates when we need to make products. We have a fairly good Young's modulus, usually around 1 megapascal. We have a good maximum elongation, and we have fair dielectric losses as well. But then when we are up against acrylics and how much they can actuate, we really fail on the dielectric permittivity and the electrical breakdown. The dielectric permittivity probably being the most important optimization parameter in our field. And when we talk about the optimization, then we usually go out from the actuation equation derived by Pellerin et al. In the late 90s and early 2000, where they coupled our strain, so that is the displacement we can get out of the material, for a given electrical field, so that's the voltage we have, and D is the thickness of our film. And then we have the dielectric permittivity and the Young's modulus. So more or less, if we look on the material, of course, we can change the thickness of the film in the processing. But with respect to material parameters, then we have the permittivity, the Young's modulus, and then also the electrical breakdown strength, which is the ultimate voltage we can apply over our material. So in 2004, together with Peter Sommer-Larsen, we derived this figure of merit for the dielectric elastomer actuator material, where we sort of coupled that we had the dielectric permittivity over the Young's modulus multiplied by the electrical field squared. But this equation somehow forgets a lot of important parameters for our dielectric elastomer performance. For example, I think the most important is, do we have conductivity in our material? Because then we don't really have a dielectric elastomer. And actually some of the material that's been shown as dielectric elastomer prototypes at least, they have actually shown conductivity, which means over time we will see the material leak a lot of current. But then on the other hand, we have dielectric loss, we have mechanical loss, and we did some work on including that when we had to account for how good is a material. Can we make it very lossy and still claim that we have a good material? And that has been done so far because every single comparison has been made based on this. So therefore we included these losses so we could make a better comparison than before. So in our recent review, we looked into what has been done in the literature in order to enhance mainly the ratio, the dielectric permittivity over the Young's modulus. And we could, of course, start out just making our silicone elastomers from commercial silicones or silicone elastomers. But also work has been done on seeing how does actually the cross-linking chemistry work. Can we use hydrocellulation, condensation, UV curing, and so forth? And will it alter the properties? And then also, I think one of the most important issue we raised in the review was to tell people a bit about the mixing ratio, the cross-linker polymer ratio. To get really nice actuation is actually by cheating and not adding enough cross-linker. Then we get back into the problems we see of the VHB tapes. Then there are other, we have sort of grouped them into silicone composites, silicone polymer blends, chemically modified silicones, and systems with complex structures, and I'll just give one slide for each of them and tell about good and bad things. So silicone composites, I think that's the most commonly used method. It's simply taking a commercially available silicone elastomer, mix in methyl oxides of various kinds, and then we have an improved dielectric permittivity, but usually the ratio of our dielectric permittivity over the Young's modulus is not improved. It's more or less constant. Then for an actuator, that is sort of, it doesn't make any sense to add in the particles, But on the other hand, if we look on the generator mode, then a high electrical field breakdown strength is very good to have. And the harder we make our elastomers, actually the better breakdown strength we get. So there is a possibility to use these silicone composites for generator materials, but not really for the actuators. And when we do work with compositing of the silicones, then we enter into a lot of problems in the process of the films, because we get a very high viscosity, and we need to add a lot of solvent in order to make our films possible to cast the films. And then what we realized was that the solvent, we really had to do a lot of extra work in order to be able to remove the solvent. Here is just shown, we cure our elastomer, and then we have our stress strain looking like this. We have a soft and compliant elastomer, and then we remove a few percent of our solvent, and then suddenly we have a much more stiff material. So we spend a lot of time figuring out how to remove it efficiently, how to figure out if we actually removed it. So we also had the idea, instead of adding these hard, rigid metal oxides into our systems, we would like to have some soft materials embedded in the material. And we spent a lot of time initially actually microfluidic devices, and we made these very nice capsules. So we have a silicone shell around the liquid, and then the silicone shell could be reacted into elastomers, but the process was really tedious. And then after a year of hard work, Piotr Mazurek, he figured out he could actually just mix in the glycerol, speed mix it, and then we got very similar materials, but just from one pot experiment, more or less. And we could simply increase the loading of our glycerol, and then we would just have more droplets with approximately the same size. So that was a way to get an increased dielectric permittivity without getting an increased Young modulus. Blending in high permittivity substances is actually, sounds really, really easy, but it's very complicated, because silicone polymers, they don't really like any other materials, more or less. So here we have just added in an aromatic substance into the silicone. We speed mixed it. Usually that's sufficiently to make sure they are homogeneously mixed. But then after casting it, it was obvious. It's actually a picture you could see with the naked eye, that we had this kind of phase separation. Of course, when you see it on this scale, then you get a clear indication of how bad it is. But on the other hand, we tried then to work with some more miscible polymers. So we have a chloropropyl silicone oil with a few of the methyl groups replaced by chloropropyl groups. And here we have 30 pHr of the chloropropyl oil in our silicone elastomer matrix. pHr, it's parts per 100 rubber. And here we could get nice homogeneous properties. But then when we have 100 pHr, so that is 50% by volume of the oil, we actually still had a very nice elastomer, but we could see from a microscope image, so that's actually the width of the film we have here, that we had very much phase separation on the local scale. So I think every time we proceed with making blending in, we need to spend a lot of time analyzing, do we have phase separation? Will we get phase separation when we start stretching our materials, and so forth? So a very easy approach to do, but on the other hand, I think we spent the same amount of time making sure it actually works afterwards. Click chemistry was then a way where we can introduce non-miscible substances into our materials and making sure that they stay. So the final target was that we wanted to make an aceto functional silicone polymer, where we could then, by mild condition, click reagents into our elastomers, and then we could simply get different moieties on our silicone backbone. Of course, it's a bit tedious. We go through a lot of steps in order to make the aceto-functional siloxane. But on the other hand, then we are sure when we have made the polymers that we don't have any large-scale phase separation. Of course, these groups, they can agglomerate, and that's also what we saw, because we actually, for this type of elastomers, we realized that very small concentrations were very favorable, but when we went higher, we didn't actually get any improvement of our properties. And that we actually explained by simply having the phase separation on a nanoscopic level. Oh, I should say the click chemistry, at some point we simply thought it was too tedious, but as I'll come back to later, there are actually very good things about having the full control over the chemistry and thereby also of the elastomer. So it may be worthwhile using this approach. Then we also said instead of improving the dielectric permittivity, then we look on the Young's modulus as the sole optimization factor. And we played around with making bimodal networks. So what we did was we took a short silicone polymer and a long silicone polymer. We cross-linked it below the gelation threshold such that we got very hyperband structures illustrated here and here. And then we reacted them together by mixing the two mixtures. And we got materials that look like these. The blue ones are actually just fluorescent molecules such that we could see if our hypotheses, they held. And what we get out of this is, when we do it this way, we get a very heterogeneous material with respect to the Young's modulus. So the blue, they are very low Young's modulus, and the red are very high. So we get a matrix with very low Young's modulus, and then we have the reinforcing red points in our matrix. If we just mix in all our components at once, we see that the picture, of course we have some distribution in the local Young's moduli, but on the other hand, we don't have such a significant difference, because here we simply change from blue to red, and we don't really see these transitions in the traditionally way of making elastomers. Again, it's very tedious. We don't get any improvement in the dielectric permittivity, but we can actually decrease the Young's modulus by around a factor of 10 to 20. So in order for all our model development, our film production and so on, we need to have some reliable data. We can make reliable models and so forth. But what was very obvious when we did the review was that data was really, really scattered. So here we have taken 50 different films, silicone films, from different studies where we have taken out their best composition, and we then plotted various things. So this is the Young's modulus as a function of breakdown strength, and here we have the relative permittivity as a function of breakdown strength. And it's very obvious here that, okay, with the red line, I've made a least square fit, and we can make a fit, but it's not really a fit that says anything. We have all the outliers here. It goes a bit better when we have the relative permittivity. We can sort of say when we move up here, we have higher relative permittivity. We have added a lot of dipoles. Then we usually have a less homogeneous material, and then we get a lower electrical breakdown strength. But from this, it was really obvious to us that if we wanted to proceed and we wanted to make models that couple, for example, electrical breakdown strength to for example, the Young's modulus, then we needed to be sure that all other scientists, some of our data is actually also scattered, but it's very important that we follow standards, we make sure we produce our films and also make our elastomers in a reliable way. So how do we actually ensure that? I think the first part is actually say, if we don't hand over stable formulations to the process, then we will actually just carry the monkey with us. And I think the monkeys will multiply each time we sort of make a mistake, and we hope somehow the process will repair it. But in the thesis, I've talked a lot about a lot of different things, but I think if we just sum up the three most important is when we make our formulations for the elastomer, we need to be sure we don't have any phase separation. We also need to look into, do we have an efficient curing such that we maintain the elastic stresses in our materials? And then also the very important one, that we shouldn't really cheat with the stoichiometry to get a soft material. Then we get something like the material I've illustrated here. But what is also very obvious is that suddenly we don't have like a full material. We have sort of lumps and things falling out. Of course, in a dielectric elastomer, we won't have these big lumps falling out. But on the other hand, we can have small pieces of our elastomer film being taken apart. Then we proceed towards the stable processes, and there it's very important we don't build up any residual stresses when we coat our films. And as I also talked about, especially for the composite, we need to be sure that we get all solvent removed. We can just see that by a few % of solvent remaining in our elastomers, we really get a significant change. I showed it in the Young's modulus, but also in the electrical breakdown strength. And if we, for example, take our films, we coat them and we make them into products immediately, then of course the solvent will never really have a chance to leave the product afterwards. Then I keep talking about we should go through, we should formulate reliable, we should also process our films, coat them reliable. But how can we actually then be sure that they are reliable? And we realized that actually we could gain a lot of knowledge from the Weibull distribution. So what we do is we take the electrical breakdown strength of a material, we test the highest voltage we can apply before we have a short circuiting in 10 to 20 places along a film. And then if they fulfill the Weibull distribution here shown by the probability density function, then we have good data. I've shown here, but I'm actually running a bit behind time. But it just shows that we can use these distributions, we can compare them to others, and depending on how narrow they are, we can see if we have a reliable film. We have made films that we knew were not homogeneous, and then we can see we sort of have good and bad parts, and they will give the width in the distribution. Stable elastomers, of course, they shouldn't really break down electrically or mechanically, but usually the problem for dielectric elastomers is a mechanical or electromechanical, coupled electromechanical breakdown. But when we look into the large products where we have a lot of films assembled into products, then the problem is actually we have an electrical breakdown, it burns a hole in the film. But then usually when we have our material, we will have a stress over the material, a mechanical stress, and then we will just see that we have a stress propagating from this area through more or less the entire product, and then the product will fail. So all these residual stresses, they are actually solidified areas, and then we of course have a huge stress gradient between these threads and the silicone matrix, and here we will see the crack formation happening. And I talked about the chemical modification. We worked with some of our elastomers. We looked into how the breakdown zone would look. We don't have any stress on these materials, but the reference elastomer clearly has the threads going out. We also see it for this CO2, so it's a chloropropyl copolymer cross-linked into an elastomer. It has the same tendency. But then when we have intermediate concentration of the chloropropyl group, so these two are actually identical, this one just has the double amount of chloropropyl, then we see that suddenly the breakdown zones here, they have changed. It's sort of, there's a lot of things happening in a circle, but then we don't have all these threads around, and we avoid the tearing afterwards. We looked into that and we wondered a bit why it looked like this, and we have used labeling of the different components, and we can actually see we have, after the breakdown in this zone, we have a lot of boiling. We can see droplets forming here, so they are actually chloro-rich domains, and we are looking into how we can actually couple that to what is going on. But it means that this particular copolymer actually has the capability of taking up energy such that we don't have the energy dissipated out and out into the tear propagation. So the perspective I gave in the thesis was actually that we really need, instead of just thinking about the dielectric permittivity over the Young's modulus, we need to focus on knowing the specification. We spent a lot of time in 3-4 years when we had our big project together with Danfoss Polypower, trying to solve all the problems in one material. So we would say, okay, we have the same material, it's for actuators, it's for generators, but it definitely didn't really work. We had to compromise all the time. So I think what we should do in the future is simply make elastomers for specific applications. The second step is that we should formulate our elastomers to fulfill these given requirements. And then when we formulate them, we also need to take into account that they should actually be able to process them in an easy fashion. And then, of course, when we have our processing, we also need to focus on that we don't, for example, introduce some sort of anisotropy in our materials. Scientific perspective, of course, I've talked about, okay, we don't want the tearing to happen. What if we could make a solution which could actually heal all the cracks? We could maybe put our product in the oven for some time, and then it could self-heal. And that's what we've shown here by using some ionic networks. And then we can see we actually have healed the fractures. The same is shown for this. But there is one thing about this approach. It is when we have the self-healing region, if this material is not comparable to the matrix property-wise, then we will see the breakdown taking place in exactly the same place again. So we are working on this now, but what we see is actually that if we just lose, for example, 5% in material properties here, then we just have the next breakdown and we will see a cascade and we end out being where we were initially, more or less. But it's doable. We have made now some solutions where it actually becomes harder, and then we don't see this breakdown. So the conclusion is that chemical synthesis regain its importance in the design of elastomers. I've used this as a title because, as I said at some point, I thought we just had spent too much time on chemical synthesis. It was in the formulating that we could get the good properties. But the chemical synthesis allows us to get high permittivity. We can have mechanical and electrical stability. And then, of course, if we can work further on understanding with that specific copolymer, we could control the electrical breakdown mechanism. We could go towards a lot more reliable films. Then also, reliable processes are vital. We have to have our elastomer formulation should be stable. We have the processing, and we also need, in many instances, to focus on the post-processing of our materials. And I didn't talk about it in the presentation, but the mechanical equilibration is actually just a very simple procedure in order to be sure our material will also behave, always behave the same way, is actually to stretch it to a very large extent, because then all our materials will behave identical. Then the acknowledgement, I would like to thank Peter Sommer-Larsen and Mohammed Ben-Slimane for teaching me a lot of things on dielectric elastomers. They've been a great inspiration, the both of them. Senior scientist Luna Yu is the one who makes sure that I forget that it's actually hard work doing experiments. I don't know, I just say to them, go out, do it, and then they do it because I have Luna fixing all the experimental problems. Then I would like to thank former and present students and colleagues at DPC. Frederikke Barth Madsen, she did the chemical modification, but she was so kind to proofread my thesis. Then all the PhD students mentioned and postdocs mentioned here have contributed to the work in the thesis. I would also like to thank Professor Ole Hassager for giving me the chance of doing a PhD in this department. Anders Ladegaard and Søren Vilstad are acknowledged for helping me a lot with the chemistry, so I dared moving beyond stillation chemistry. Katja Yankova read the first version of my thesis. And then, of course, I would like to thank DPC in general for providing such a great research environment. And John Willersen was actually the one who sort of got me hooked on this idea. He kept saying it was a good idea, it was something everyone should do. So he also deserves an acknowledgement. And Kim Dam Johansen, my boss, was actually the one who kicked me once in a while and reminded me about deadlines. So thank you for keeping me working. Major collaborators, Mike Brook has helped a lot with the chemistry during the last couple of years. Raimund Gerhardt with high voltage characterization. Gugi Kofod helped a lot with the discussion about reliability. Ramona Mathieu from DTU Sen have helped a lot with many of the images I've shown. And Peter Morsius at TU Delft for helping us with electrical characterizations. And then my kids, they also deserve a great thank you for their patience. And then I think most of their question was actually about all this work for a diploma. They would expect a medal or something. Yeah. And then finally, the acknowledgement for the funding, which came from Innovationsfond Denmark, the Fri Forskningsråd, DTU Kemiteknik, Dansk Polypower, Malaysian government, DTU Proof of Concept, and recently from SBM Offshore. Yeah. Any questions?